to another episode of the Corrosion Journal interview series. My name is Sammy Miles, and I'm the Managing Editor-in-Chief of Corrosion Journal, which is AMP's peer-reviewed scientific journal. Today, we welcome Winston Revie as our guest. Winston is Corrosion's longest-serving associate editor. Thanks for joining me today, Winston.
Well, it's a pleasure. Glad to have the opportunity.
So many of our listeners will recognize your name from several books you've co-authored and edited over the years, including Corrosion and Corrosion Control, An Introduction to Corrosion Science and Engineering, ULIG's Corrosion Handbook, as well as the Oil and Gas Pipelines Integrity and Safety Handbook, which are household staples for many in the industry, but they might not know much about your story. So to start with, could you tell me a little about your background? How did you first get into corrosion?
Indeed, I'd be glad to discuss that. So I was studying metallurgical engineering at McGill University in Montreal in the 1960s. And about a year or so before I was due to graduate, I started to think about what I wanted to do after graduation. And I decided I was going to do some kind of postgraduate work and probably get a postgraduate degree, a master's or a PhD, or maybe both. So at that time, I found that there were a few articles coming out in journals about the use of metals in the human body, like for surgical implants. And specifically, I remember an interesting article in the Journal of Metals in 1964 by Ludwigson, who at that time was at the U.S. Steel Applied Research Lab in Monroeville, Pennsylvania. And his article in the Journal of Metals was about the use of prosthetic metals in the human body. And I thought, man, this sounds like interesting work. Clearly, there was research going on in this area. So I wrote to Ludwigson and asked him about where a person could study this kind of stuff. You know, if you wanted to do postgraduate studies in this area after getting a bachelor's degree in metallurgical engineering, where might one go? And one of the he wrote back to me, and he gave me a list of I think 3 or 4 universities where this type of work was done. One of them was Rensselaer Polytechnic Institute in Troy, New York.
Okay.
So I wrote to them. I wrote to RPI in Troy and ended up going down and meeting with Norbert Green, Professor Norbert Green. His wife also worked in the lab there, and spent a day at RPI in Troy, and they took me to lunch, and at the lunch, Professor Green asked me the question. He said, well, if you want to do work in surgical implants at RPI, that means working in corrosion. Are you interested in this? Working in corrosion? And I said, oh, absolutely. It sounds like a great area. It sounds exciting, in fact, studying corrosion inside people. Actually, it was actually inside animals, we weren't actually working on people. So anyway, that's how I got into corrosion. And from then on, I studied corrosion, went down to RPI, and I worked on fascinating work with the Albany Medical Center, a collaborative program between RPI and the Albany Medical Center with the orthopedic surgery department at Albany, and did this work on measuring corrosion rates in dogs and rabbits using some recently developed electrochemical techniques. So that's how I got into the area, and it was really an exciting bit of work. And anyway, if I can go on and say, when I started there, the day I started at RPI in August, I think it was, of 1966, there was another student who also started that day. He came from MIT. He had done a master's at MIT and was coming to RPI. And so after discussion with him, I thought, gee, MIT sounds interesting. Maybe I should check into it. So I did. I went down to Cambridge, Massachusetts, and met Herb Uhlig, and saw the lab there, and Herb encouraged me to apply, and so I did. So after finishing my master's at RPI, I went down to MIT and started on a PhD program there, which I completed, working on fundamental aspects of corrosion, largely of copper when stress is applied and the effects on strength. So towards the end of my stay at MIT, I started wondering, well, what am I going to do once I've got the PhD? And I had an idea that I'd like to do something on some fundamental study on corrosion. One of the well-known electrochemists at that time was John Bockris. And Herb Eulig mentioned to me, when I discussed this with him, he said, well, you know, Bockris is moving to Australia soon. I think he's going in a few months' time. And I thought, well, that's the end of that. But after thinking about it for a while, I thought, oh, you know, he's going to Australia. That might be interesting. A trip to Australia and working in Australia. It sounds exciting. So, I wrote to Professor Bockris at the University of Pennsylvania in Philadelphia, and he asked me to come down and have an interview there. So I did. I went down to Philadelphia, and so he had pictures of the Flinders campus around his office. It looked like a very nice place. And Flinders, of course, was just on the outskirts of Adelaide in South Australia. Sounded like a wonderful climate there. He was going to do some research. And I told him, yeah, look, I'm interested. Let's pursue this one. So once he got to Australia, he wrote back to me offering me the job. And to make a long story short, off I went to Australia with my PhD from MIT and spent a couple of years at Flinders. Now, Flinders, University of South Australia, was a new university at that time, and everything was brand new equipment and new everything. So it was very nice there. Anyway, after a couple of years there, I thought, now, once I finish this postdoctoral here, what am I going to do now? And there was a lot of interest at that time in solar energy. And the Australian National University in Canberra had a project that was starting up on solar energy. And I thought, well, maybe this would be interesting to do. Solar energy, background in corrosion and electrochemistry. Gee, this sounds exciting. So I did have an interview there, and yeah, they offered me the job, and then I was in Canberra. And that was great. Working on solar energy. It was a program that would use a high-grade thermal energy, and that would operate a boiler system to produce electricity. Anyway, it was really more work that was sort of ahead of its time. In the 70s, in the US then, there was the oil crisis, and there was a lot of interest in solar energy. But over the decades, the interest waned a bit until just the present, fairly recent times when solar energy has really come into its own. But anyway, while I was down in ANU, I decided I was going to come back to Canada, and eventually did come back. I worked for a few months at HSA Reactors in Toronto, a company of Sankar Dasgupta, which is still in business actually under a different name, Electrovaya. But anyway, there was a position in the federal government at Natural Resources Canada, or Energy Mines and Resources in those days. And so I ended up coming to Ottawa and spending 33 years working mainly on oil and gas pipelines, which had its own excitement over all those years. So that's a little bit of history. And I retired in 2011, 10 years ago, and I'm still working on corrosion, editing books and keeping books up to date and doing some consulting work.
So you've mentioned a few different industries here, between implants and solar and oil and gas. How have those fields changed over the years? For example, I know you mentioned with solar, it was groundbreaking. It was new in 60s and 70s. How is that different from the research being done today?
Well, today, research is very focused on applications. In the 60s and 70s, and in that era, there was still a lot of very good fundamental research being done. And in corrosion, the fundamental research has actually been helped by the development of very advanced systems for microstructural characterization, microscopes and different techniques for characterizing microstructures. The corrosion area has become, I'd say, a little bit more sophisticated in terms of the equipment requirements today. Now, the industries themselves sort of come and go. Like back in the 60s, there was a certain amount of interest in surgical implants and materials used in medicine. Life magazine in the 1960s had a really big article, and the cover, I think, was devoted to, I think it showed a model of a person with all these different implants in it. But today, that type of research has really expanded. I mean, today, most metallurgy and material science departments have somebody studying biomaterials. And there's a major international conference that's held every few years on biomaterials. So solar energy was exciting back in the 70s, a lot of interest in it, but then oil really, it didn't disappear. We didn't run out of oil. And the price of oil came down actually a lot. And so it's really just recently that the environmental movement has really taken over, and the price of oil is fairly low at the present time, but because of the climate change considerations, the renewables are really where there's a lot of action today.
Right. So, and it's interesting to see how these have changed over time. And I'm assuming, for example, with some of the biomaterials, even the alloys, not just the technologies in terms of the microscopes and things like that have changed over the years, the actual materials we're using, such as magnesium and different things, how we're leveraging those and the corrosion properties therein. That's been changing as well.
Oh, absolutely. I mean, there's some very interesting research that's going on now on surgical implants that will dissolve. And so rather than having a stainless steel or a titanium implant, say to fix up a broken bone, and then having to remove that implant once the bone is all healed, you might be able to have a type of magnesium alloy implant that would last as long as it's required to last. And in time, it would just dissolve. So there's quite a bit of research going on in that area. And also in all kinds of areas where there's demand, because people are living to an older age now, and so, like for repairing hernias, polypropylene mesh is frequently used. And so that stays in a person forever, normally. And but the materials are evolving. I mean, there's artificial skin that I think is being studied now to help burn victims. And materials research in medicine is actually quite important today.
And so the largest portion of your career you've spent working on oil and gas and pipelines. Can you elaborate a little more about how the industry's changed during the decades that you spent working on that?
Indeed. So the oil and gas industry, specifically the pipelines, they're made of steel. Pipelines are made of steel, these high strength, low alloy steels. And the developments of metallurgy have made it possible for the pipelines to operate at higher pressures and use less steel. There has been a great interest in using higher and higher strength steels, because if the steel is higher strength, you can use a higher pressure. And with higher pressure, you get more natural gas that you can deliver in unit per per unit time. So if you have a high strength steel, you use less steel because it's stronger. You have a higher pressure in the pipe. And because there's less steel, the transportation costs off to remote sites where the pipeline has to be assembled is less. And there's less material to weld. And so you save in all these different ways. There's also some downside because higher strength steels are less forgiving in terms of defects. The critical defect size for the higher strength steels is smaller than for lower strength steels. And so there's a quality control and a whole issue about monitoring the corrosion of these steels or inspecting the steel for corrosion and defects. So over the years, inline inspection is one of the major areas that's really been developed so that pipelines can be inspected thoroughly and with confidence that defects are going to be picked up during the inspection. So there's inspection, which is done every few years, and then there's monitoring, which is done continuously all the time. So those two areas have really been developed. The other thing that's affected the pipeline industry is the public awareness of pipelines. There were a couple of major failures which caused the pipeline to become, caused the industry to be very much in the public knowledge. And so the combination of the background of a couple of unfortunate failures, plus the tendency of the public to really question the use of fossil fuels that produce CO2 and other greenhouse gases has really had a big change, a big influence on the oil and gas industry.
Right, which makes sense. And goes back to that emphasis on all the renewables that we're seeing in a resurgence lately.
Absolutely. There's there's hydroelectric power, and there's solar, there's wind, there's geothermal, and if you can harness all of those, then you really got quite an array of options for energy.
Right. I'm going to pivot real quick because I want to make sure to take a moment to share some of the contributions with our listeners that you've had in the field. You've been recognized as being instrumental for initiatives such as being a founding trustee of the Canadian National Capital Section of NACE International, a founding president of the NACE Foundation of Canada, a founder of the Banff Pipeline Workshop, BPW, just for a few of them. And I know with that biennial BPW conference that you started in '93, it brings together industry personnel, regulators, service providers, researchers, and other stakeholders to identify industry issues and provides a platform to develop and deploy solutions, which is of utmost importance. As you're mentioning through some of your comments, we need to bring people together and discuss different things and how to make it better. For these contributions and others, you've been honored as a fellow in a number of organizations such as NACE, ASM International, and the Electrochemical Society. With that said, what do you feel is your greatest contribution to the field?
Well, that's really for others to judge from their own perspective. Some people might think, well, that work I did on the surgical implants back in the 60s was new and different from anything else. They might think that was the greatest contribution, but others, who come to the pipeline workshops in Banff, the last workshops have had between 800 and 1,000 people in attendance, and some people might think, well, maybe developing those workshops or establishing the workshops was the greatest contribution. So different people might have their own view on the relative merits of separate contributions. We did indeed set up the Canadian National Capital Section of NACE International in the 1990s, And that was certainly it was a great it was a really interesting thing to do, because it brought together all the people in the corrosion area who were working in the Ottawa area and surrounding vicinity. Until that time, we had the different corrosion labs in Ottawa, but we didn't actually have a venue for meeting regularly. And so establishing the section here was really a great advance, actually, because it served as a venue for all of the corrosionists in the area to get together. And we've had some very interesting conferences here since we set up the section.
Great. And hopefully they continue as we or move into a virtual platform in the short term, until we can get back to having in-person meetings.
Well, yes,
Dialogues.
that's right. I hope we can start having them soon, actually. But in Canada, of course, we have our own schedule for vaccinations, and I don't think the schedule's been totally worked out. I heard President Biden talking last night. Actually, he had a State of the Union address, or he had a public address, and he was optimistic.
We'll get there.
No doubt.
Yeah, right. So what advice do you have to the industry?
Well, for corrosion, there are really four things. First of all, what we learned in the 60s, actually, when I started studying corrosion at McGill, was design corrosion out. Make the best design that's possible so that corrosion won't have the opportunity to work its degrading effects. So design it out. A combination of materials design, process design, cathodic protection, inhibitors, and coatings, okay, all design. Then the second thing is inspect for corrosion as frequently as necessary, and maybe develop a model for the development of corrosion so that you may be able to predict the crack growth rate or defect growth rates, and decide on what the interval needs to be between inspections so that you don't reach the critical defect size that leads to failure fairly quickly. Okay, so inspect and have a model for the corrosion development so that you can predict the time required between inspections. And then beyond inspection, there's monitoring. So that's continuous monitoring. Like for pipelines, I think they'll have aircraft flying over the pipeline relatively frequently to monitor any gas that's being emitted from a natural gas pipeline, or to look at the change in snow cover on the ground. And if you can see that the snow is melting, well, maybe there's something coming from the pipeline. So that's the third thing, monitor. And then the last one is engage a corrosion specialist to review the plans and the procedures for construction, operation, and maintenance, and to be able to assess the data from the inspection and monitoring during operation. So 3 things: design, inspect, monitor, and engage a corrosion specialist who can add expertise.
Wonderful. And on a more personal note, what advice do you have for people to excel at their jobs in the corrosion field?
Well, okay, good question. I think that as a person settles into a job, he or she would over a period of time, personalize the job to their own unique expertise. Like corrosion is a multidisciplinary area, and it involves metallurgy, involves chemistry, and different branches of chemistry. There's organic chemistry for inhibitors typically, and also there's physics involved. So depending on a person's background, they're going to have their own unique contributions to the area. And it's really, what I think is that it's what you do over and above the minimum that's required in the job description. Like the job description specifies the things you do. Now, when I established the Banff Pipeline workshops, there was nothing in my job description to say, I was supposed to do this, but it looked like something that needed to be done. And it worked out that it has been very popular in terms of
Mm-hmm.
attendance. So my suggestion is to go above and beyond what's in the job description and personalize the job to your own unique capabilities. And for the manager who's trying to assemble a team on corrosion, my suggestion would be to, because corrosion is so multidisciplinary, get people with backgrounds in the different areas. Like you could have, somebody with a chemical background, a metallurgical background, and maybe a physics background, and maybe different sub backgrounds. So that all the different areas are covered off, or most of them anyway, on your team, rather than just having a group all with a chemical background or all with a metallurgical background, because of the distinctiveness of corrosion as such an interdisciplinary or multidisciplinary subject.
I think that's great advice. And I think that would help managers, and I think that helps individuals in the field try to make the most out of their career and enjoy it to the fullest and be the most successful at what they do.
Be the most successful at what they do. And
Mm-hmm.
just to put in a positive word about corrosion as a career to get into, I don't think I have ever met a person who works in the corrosion area who wasn't really satisfied with his job, or satisfied with the work he was doing. My suggestion to people is that they need really to like the work that they do. And from what I've seen in corrosion is that people in the area seem to be happy with what they do in corrosion. So there's well, whether they're doing failure analysis or whether
Mm-hmm.
they're designing things to prevent failures. Um, I think that the corrosion does offer a rewarding career that people in the field, I think, tend to appreciate.
That's fantastic. Now we're getting towards the end of our time, so I want to ask real quick, if any of our listeners want to get in touch with you, what is the best way for them to reach you?
Yep, write me an email, send me an email, win25@rogers.com. So win, the first three letters in my name, Winston, win25, the number 25, at rogers.com, WIN25 at ROGERS.com.
Perfect. And before we sign off, I'm going to borrow a feature from the Coatings Pro interview series podcast. Coatings Pro is one of our sister publications here at AMP, and they've launched rapid fire questions, which provide our listeners with an opportunity to get to know our guests a little better. So with that, who is your hero or mentor?
Well, I would say that the one I appreciated the most was Herb Eulig, actually. He and I did a lot of work together after I completed my PhD. And I learned about his meticulous nature and how he proofread the publications, proofread the book, actually, by reading it aloud. I spent many hours with Professor Herb Eulig at the International Conference on Corrosion Fatigue at Storrs, Connecticut. I think it was in 1971. And we read the book aloud to do he had the final proofs in his hand, and we took turns reading aloud. And he went through all the proofs and picked out the typographical errors and made final corrections in the proofs. This was certainly a very thorough way of going about things, and a way that I hadn't actually seen before. But it's informed my own sort of habits, I guess. I tend to be a bit meticulous in the editing process and checking things to make sure they're right. A few years after I had finished my PhD with Herb Eulig, I was in the office of another scientist as he received a call. He received a telephone call from an editor who was asking about where the final proofs were and the corrections.
Mm-hmm.
So this particular scientist just flipped through the pages. He with the editor on the phone, flipped through the pages, and he said, "Right, looks good to me. Go ahead. No corrections."
Wow. Big difference between those two styles.
Absolutely.
Excellent. So the second question I'm going to ask is, what is your biggest pet peeve?
needless bureaucracy and paperwork. Of course, we're getting away from paperwork to a certain extent now, since a lot of it is done, a lot of the bureaucratic stuff is done online. That helps a bit, but still, I think we could cut down on the bureaucracy a bit and just get on with the actual work and the research.
I think most of us will agree with that one. Well, with that, thank you so much for taking the time to join me today.
Well, it's a
And
pleasure.
fantastic.
Okay.
I'm Sammy Miles, and again, I'm here with Winston Revie. Thank you for listening to another episode of Corrosion Journal's interview series. If you want to learn more about the journal, make sure to visit corrosionjournal.org. You can subscribe to AMP podcasts if you haven't already on Apple, Google, Spotify, and all the major distributors. You can find all episodes of AMP podcasts on amp.org. That is ampp.org. And we'll be back soon with another episode. Thanks for listening.